Radar 10, wind waiting on 3.
Okay, this is radar, standby. I'll need 36301 first.
Roger, ready to send 301.
Waiting data.
Sending now.
Receiving data. Okay, wind wait, that's good. I'm ready for 36303.
Ready to transmit 303.
I'm waiting for data.
Sending now.
And receiving. Okay, that was good. I'll need 36304 next.
Roger, ready to transmit 304.
Waiting.
Sending now.
Receiving.
Did someone call receiving? Did someone call receiving? Channel 4?
One weight radar, this looks good. I'm ready for 36306.
Roger. Ready to transmit 306.
Waiting
Transmitting now.
and receiving. Thank you.
Roger.
Good evening. I'm Linda McGilvery, broadcasting live from Poker Flat Research Range, and with me is Dr. Roger Smith, Director Emeritus of the Geophysical Institute and Professor Emeritus of the University of Alaska, Fairbanks, Department of Physics. Welcome, Roger.
Thank you. I'm glad to be here. It's exciting tonight.
It really is. This is actually day 6 of the February sounding rocket campaign at Poker Flat Research Range. And Doctors Christina Lynch and Robert Pfaff are sharing this launch window, and each expect to be launching 2 rockets for their respective missions. Tonight's launch window is from 7 p.m. to 1 a.m. Alaska Standard Time and 11 p.m. to 5 a.m. Eastern. And we have a video we'd like to show that describes Dr. Lynch's ISINGLASS mission. And she is the researcher whose mission is prime tonight, which means if conditions are appropriate, her rocket will be launched first. So let's go ahead and play that video.
I've spent many nights So my name is Christina Lynch. I work at Dartmouth College in New Hampshire. Dartmouth actually has a long and involved relationship with Alaska, and we have a large percentage of our students that come from Alaska. So it's nice to be here. I'd like to thank you for letting me share my work with me. I've been coming out to Chattanooga since the 1980s, and I've spent many nights watching the aurora from Poker Flat. Mr. Edwardson's comment about how the arc leads back to Barrow really resonated with me, because when I watch an arc that goes from horizon to horizon, I've always felt that it shows me that the Earth is round, and the idea that it is larger than we are. It has always been very strong with me. In this first picture here, you can see one of my earlier rockets, which is conveniently labeled at the top of its styrofoam box, up. So the NASA engineers were making it very clear which way they wanted it to go. But I wanted to start, if you can go to the next slide. Yeah, so you should be seeing a movie from the space station. I just love these movies that the astronauts take from the space station. We spend so much time looking at the aurora from the ground, and so to have the opportunity to see what it looks like from above just really changed my view of what I was looking at. We see our own little picture of it, what's above our head, but it's part of a much larger system, and that's something that I just find very beautiful. So I could watch this movie all night long, but we should probably proceed. So you can go ahead to the next slide. When people ask me about the work that I do, I say that the science, the physics of what I study involves three core ideas. Electricity and magnetism sets the rules of why the aurora works and how it connects itself. The plasma, which is ionized gas, so particles with their electrons stripped off of their atoms, those are the things that respond to the electricity and magnetism. And the geomagnetic environment that you've seen earlier today, that's where it happens. And you put these three ideas together and you have the auroral system. So we can ask ourselves, why would you want to study this? How would you go about studying it? And what do you learn when you've done? So when people ask me why I study the Northern Lights, my first answer is always that they're beautiful. It's such a privilege. We tell each other, I can't believe they pay me to do this job, right? We get to come up to Alaska and spend night after night watching the Northern Lights go by and waiting for them. Scientifically, though, they're a fundamental plasma physics laboratory. Plasma physics is the essential physics which rules things like fusion machines, astrophysics, the basic rules of how our universe works. And the Northern Lights are right here, and we can study it. And so if we understand and can learn more about how the aurora works on our Earth, we can take that information and use it to understand what we see even on other planets. And so the next slide shows a still. There's actually much better images of this now. But here is Jupiter from Hubble. And if you look at the top and the bottom, you see there's aurora. So there's aurora on Jupiter, there's aurora on Saturn, and understanding close up how the aurora on our world works helps us understand how other planets work. So the next question you can ask is, how would you study them? And so there's lots of different ways to view the aurora, including Liz's citizen science program, which is just lots of people getting together and sharing what they know. For our more particular studies, we can look at the aurora with cameras, imagers, radars. If we go into the place where the aurora is, we can study it with satellites and rockets to actually measure the fundamental plasma physics that's causing those lights. My own particular work is very interested in trying to quantify the structure and how the aurora dance and move. And to do that, we want to use what we call multiple point missions. And so for the ISINGLASS rocket, we've been working on using what we call low resource, so we're actually using Arduinos to try and have many payloads. So our ISINGLASS mission has 2 launches into 2 auroral events to 350 kilometers. And each one has an array of 6 payloads. So if you could start that little movie. So you see 1 payload separate, and then 4 little payloads will come out. There they go. And then that whole array of multiple points is going to move over the aurora that we're trying to study. And so I wanted to say 2 separate things here before I leave this slide. One is I'd like to extend my very, very particular grateful thanks to the village of Venati. The village of Venati is right under the place where our rocket will reach its highest point. and they are very kindly hosting several of our students and a great many of our cameras. Because Venati is underneath where the rocket is going, if we put cameras there, we get an excellent view of the particular aurora that we're trying to study with our sounding rocket. So my students and science team have traveled up there today. They'll be setting up the cameras, and then we'll be sending students up until we launch to monitor the cameras and send the information back. So we're very grateful to the village of Venati for allowing us to do that. The separate thing that I would like to say is, if you look at the aurora, you see it all moving around. And so the core part of how I'm trying to study the aurora is to measure that structure. And the example that I always use is to say that you had a reporter by the coastline, and there were to be a tsunami. And over the course of a week, she moves away from the coastline. And she writes back to you and she says, oh, it's getting better, it's getting better. Well, you don't know if it's getting better because it's been a week or because she's moving away from the coast. But if you had an array of reporters all at different distances from the coast, and over the course of the week, they told you how the situation improved, you would be able to separate the effects of space, position, from the effects of time. And so with our multiple point sounding rocket for ISINGLASS, as we move through the Northern Lights with multiple probes, we're trying to measure how are the different structures in the aurora ruled by the effects of time and the effects of space. And that's what we're trying to understand. So if you go to the next slide, or we can watch this again, also good. You can see a hopeful scientist waiting on the top of the hill at Poker, waiting for the aurora to do its thing. And my last slide just shows the radio dish at the top of the hill. So we'll be waiting to see what the aurora can tell us over the next couple of weeks. Thank you.
And that was Dr. Christina Lynch, who is an experimental physicist and professor of physics and astronomy at Dartmouth College. She serves as the principal investigator for the Ionospheric Structuring In Situ and Ground-Based Low Altitude Studies mission, also known as ISINGLASS. What else can you tell us about this mission, Roger?
Well, so what is aimed at here is to try and understand how the structure in the aurora is created, whether this is created as a temporal series of things or whether it's a spatial or it's a combination of those. And in order to make that kind of determination, you need to look at this structure from several different directions. And so, as you saw looking at the film, they have a single rocket going up, but then several daughter payloads are launched out so that they can see any of the structure that there is there from different directions. And then they can decide whether or not this is temporal or spatial. This has been an argument over many years that some of it is temporal and some of it is spatial, and some people think it's all temporal and others that it's all spatial. So this experiment will answer some of these questions. And as you saw also, the region of space where they hope to do this measurement is over the town of Venati, which is just a little north of Fort Yukon. And so the rocket is going to fly up and it will reach apogee just over the top of Venati, and then they have a bunch of cameras on the ground to watch what's happening with the experiments. It's a really exciting type of thing to do. The tricky thing is, of course, that everything has to be just so before you can launch the rocket. And even trickier, if we're at T-minus 10, that is 10 minutes from the launch time, and if it takes another 5 to actually, once it's launched, to get up to altitude, then you have to anticipate what's going to happen 15 minutes from the time of launch. That takes a lot of skill and a lot of courage. So it's an exciting thing for the experimenter to do, maybe a little worrying for the experimenter to do too, because she doesn't get a second chance.
That's right. And in fact, Christina Lynch has 2 rockets that she'll be launching with this experiment that she's doing. The first one will be launched into one type of aurora structure.
That's right.
And then she'll be looking within this launch window for a second type of structure. So,
But it's not as if she has a second chance to do the same thing. In order to be successful, she has to do these 2 different types of structure. So that means that she really doesn't have 2 shots at doing this. She has one for one type and one for the other. It's a sizable task to be able to anticipate the aurora.
Now, how long does it take for that rocket to get from here at Poker Flat Research Range to its apogee above Venati?
It's going up quite a way, and it takes about 5 minutes to get there.
Okay, that's a pretty fast rocket.
It's a very fast rocket. You'll be surprised when you see it going up how fast that moves. It doesn't hang around.
So I know they've been watching the weather conditions. I understand the skies have to be clear above Venati, and then we're also looking for some things related to the aurora that they're just kind of holding and watching at the moment.
Right. Well, we are both looking. Unfortunately, the people out seeing this presentation can't see this, but what we're looking at is the sky over Venati, and we can see stars. Not much aurora now. A little while ago there was some aurora we could see in that, but unfortunately it has slid off to the north. And I'm sure everybody is hoping and willing it to come back so that we will have the condition to do the launch. I think everything else is good.
That's great. There's actually quite a team of people in the room just across the hall from us, and I know we were talking yesterday about the expertise that's represented in that room.
Well, that's absolutely true. There are many experienced rocketeers, I guess we could call them, over there in that room, and I think that you notice that the more stressful it gets, the less noise there is over there. The synapses are firing pretty fast.
Yes. And each one of them seems to be focused on a screen or some other resource that's providing data into this
That's
mission.
Right. So part of what the range does for an experimenter is to provide them with a suite of data, and in many cases a display program that will show it to them in a useful way. And that's what's going on over there.
Okay. Well, as I mentioned, Dr. Lynch is prime at the moment. There are 2 researchers who are sharing this launch window. The other is Dr. Robert Pfaff Jr., and the conditions are not necessarily lending themselves to a launch for his mission at the moment.
Well, that's right. We don't currently have clear skies here at the range. Those people who have been watching our all-sky camera have seen that there's not much to be seen because it's cloudy. And then the other range sites that they want to use are also cloudy at the moment. So Dr. Pfaff is not able to launch his rocket because he doesn't have the camera resources available.
Okay.
So we're just waiting for it to come back on south. We still have flows and we still have current, so we have electrodynamics, but we need the arc to come back down to where we are. So and Colesfoot and Tulloch are clear, so our triangulation for the beacon lights would be very good. And the Venati skies are very clear, again, despite prognostication. So, so we wait. Thank you.
Copy that. Thank you.
Okay.
So you were just hearing the report being given by Christina Lynch about her experiment, and she was saying that the aurora is too far to the north at the moment. We're hoping for it to come back, but the skies are still clear. And so she's optimistic that she may be flying the rocket pretty soon.
That's good news. We'll be anxiously waiting to see what happens here.
That's right.
Last night we had several periods of time where we thought that a launch might be possible, and things change very rapidly sometimes. So we'll hope that we have better success tonight.
That's correct. So at the moment, as you may be able to see, you may have seen, we're at T-10 and we're holding. So the rocket preparation for launching the rocket is halted until Dr. Lynch picks up the count, and then it will most likely to go to T-3, where it can hold again until precisely the type of situation occurs when it can be launched. Last night we were at T-3 twice, but it didn't subsequently launch.
Mm-hmm. So can you explain a little bit more about how the countdown works? I know T-10, a lot of people might assume that that means in 10 minutes there's going to be a launch, but that's not necessarily the case, is it?
Well, no, because although the stages that are put into the preparation for launching are meant to be about 1 minute long, they may actually sometimes be longer than 1 minute, in which case the count will be longer than 10 minutes. But they actually attempt to go through and get these tasks done a minute at a time. And if that doesn't happen, well, we're just a little bit longer getting up into the air.
Okay.
Radar 10, wind waiting on 3.
Radar 10, I see that the popped.
Roger, I see that too. You can drop track.
Roger. Would you like another?
We're good for the moment. I'll check out this data and I'll get back to you guys if we need anything else.
Radar copies. Balloon inflation, radar on channel 3.
Radar, this is wind waiting. She stepped out for a minute. We're going to hold off.
Roger. Roger.
Thank you.
Radar, this is CM on range ops.
This is radar, go ahead.
Yeah, we've got 2 test rockets loaded up and might be a good time to go ahead and get them out of here and get a little practice before things get hot.
Roger, copy. Radar's ready.
Roger that. You copy, OC?
OC copies.
And we just heard that they're going to be launching some test rockets here shortly, Roger. Can you explain what they're using those test rockets for?
Well, the test rockets are to make sure that the radar system that is designed to pick up the real rocket that we're going to fly later on is working well. So they fly this smaller test rocket as a target, and the radar is got to acquire it and follow it. And so if it does that successfully, then that's a good test. What we're going to see on the screen here, right on the far left, is where I think where they're going to load the test rockets. and they probably will fire 2, and we'll see that streak go up on this upwards from that launch point. And I don't know whether we're going to be able to put the all-sky camera onto, so you will see then the rocket rise into the sky. It'll come out of the edge of the all-sky camera, which is the horizon, and rise into the middle.
Okay, and so we'll go ahead and switch back to the range communication system so that you can hear as they prepare to launch those rockets. There will be a countdown associated with that.
On my mark will be at 10 minutes and counting for a test rocket on pad 1. 3, 2, 1, mark. We're at 10 minutes and counting.
Blockhouse is a roadblock 1, radio check.
Loud and clear.
Blockhouse is a roadblock 2 for radio check.
Loud and clear.
One is out the gate. 2 is out the gate.
Copy that.
So we just heard the announcement, 1 is out the gate and then 2 is out the gate. These are trucks which are going out to put up the roadblock so that we don't have traffic going by when we launch the test rockets. Even though these are just test rockets, they're still pretty lethal if they happen to come down on top of anybody. So we don't want that to happen.
8 minutes.
It could also be quite a surprise to someone driving by at the time those rockets go off. So.
One is in position.
Can you repeat, please?
Roadblock 1 is in position.
Copy that. Thank you. Seven minutes.
1, 2.
6 minutes.
1, 2. Roadblock 2 is in position.
Roger 2. Five minutes.
1, 2.
Four minutes.
1, 2.
Three minutes.
1, 2.
Two minutes.
1, 2.
Radar, you go.
Radars go.
Surveillance is go. LO.
Go.
RSO.
Go.
The range is go. All personnel will remain undercover during test rocket launch. 90 seconds.
1, 2.
Latest on station.
60 seconds.
1, 2,
50. 40. 30. 20. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, plus 1, 2, 3, 4, 5,
Radar's
6,
tracking.
7, 8, 9, 10. Plus 20. Plus 30. Plus 40. Plus 50. Plus 1 minute.
Impact. LOS radar.
Radar, let me know when you're ready for the next one.
OC radar is go.
Copy that. Thanks. On my mark, we'll be at 60 seconds and counting for a second test rocket on pad 1.
Copy.
3, 2, 1, mark. We're at 60 seconds and counting.
1, 2,
Surveillance is go. Radar, you go.
Radar is go.
LO, are you go?
Go.
40 seconds. RSO.
RSO go.
The range is go. $30. 20. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Plus 30. Plus 40.
Well, those two rockets seem to have gone off without any difficulties, and I know that they mentioned LOS radar, and what does that mean?
Means loss of signal. So
Okay.
they managed to acquire both of those rockets and they acquired them until they either hit the ground or went behind something, so they couldn't be seen. But they don't go very far. These rockets are going to hit the ground within a mile or two from the range.
I think they have a few of those test rockets down in the administrative building here on the range, and they're, probably about 3 feet high, just small rockets, but they do perform an important function here.
Right. So we need to know that the radar is going to acquire the experimental rocket when it's fired. So it's good. But we go through all the same procedure, as people notice, that we do the countdown and we do the checkup to see that everything's ready. And we put out the roadblocks, just like we would if it was a real big rocket that was going.
Lots of practice, lots of double checking everything, triple checking things to make sure that we're not wasting any resources that are quite valuable in terms of the research performed, also in terms of the cost of developing them and performing the experiment.
And the reliability of launching from this range is really very, very good. We've been doing this since 1969, and our record of getting a successful launch is very, very, very strong. And it is about the discipline of always following the rules, and about being prepared for anything that might go wrong, to be able to take appropriate action. But so we've, in the time since 1969, if you count every type of rocket that we have launched, excluding test rockets, we've launched over 2,200.
Wow.
But most of those were met rockets. Only about 340 of those rockets were big ones, like we're flying tonight with Christina Lynch. And so those are less frequent. We tend to launch maybe 4 or 5 of those every season. And our rocket launching season is usually January, February, March.
Right.
And it's a time chosen because it's a time when clouds are less frequent, and so we have a better chance to get a successful experiment done.
So we're midway through the rocket launch campaign for this year. There was a previous launch that occurred in January, and now there are 2 more experiments that are waiting to be completed.
That's right.
Dr. Lynch and Dr. Pfaff.
And there's a difference, quite an important difference to many people. The launch that we did in January, the rocket came down with a parachute because they wanted to recover the experiment to fly it again. Now, that makes the rocket's got to be bigger and heavier to accommodate the parachute. It's more expensive, but it is a way to recover a payload and fly it again. I think the record we have for doing that is 20 times. We've flown the same payload 20 times in one particular case. But the rockets they're flying, if we flew today, that rocket does not have a parachute. And it will just come down, it will get severely bent up when it hits the ground.
And I understand they do have a program here at Poker Flat where if someone is out hunting or is out for whatever reason in rural Alaska and they come across a part from one of these rockets, they can actually notify the range of where that item is located and they'll recover it, but they also do pay little bit of a...
There's a bit of a price for doing
price,
it. Because, you know, we try very hard to collect all the garbage that we leave around. But there are some times when we can't find the rocket part that we're looking for. And we're glad that the people in the general public are doing things to help us with that. But we do hope that the people who find parts of rockets don't stick their heads inside of them or something, you know. We're never quite sure whether all the fuel has been burnt and such a thing, you know. So people need to be careful when they find a rocket part. Probably
best just to contact Poker Flat Research Range and let them know the location of it and not try to handle it themselves.
Yeah, don't pick it up and put it in the back of your car.
Right. Well, I'd like to mention just real quickly that Dr. Lynch does have a blog for her ISINGLASS mission, and that is http://isinglassmission, which is all one word, .blogspot.com. So if anyone is interested in following the progress of the mission, go ahead and check out that blog. We're also keeping everyone updated on the Poker Flat Research Range Facebook page. We have a Twitter feed, and then there's also the Geophysical Institute's Facebook page as well. So if you're interested in knowing what the latest is, there's plenty of opportunities online for that. Well, we do have a video that NASA has produced, and that describes what is a sounding rocket, and we'll go ahead and show that momentarily.
A sounding rocket, sometimes called a research rocket, is an instrument-carrying rocket designed to take measurements and perform scientific experiments during its suborbital flight. Sounding rockets take their name from the nautical term to sound, which means to take measurements. The rockets are used to carry instruments from 50 to 1,500 kilometers above the surface of the Earth. Since 1959, NASA-sponsored space and Earth science research has used sounding rockets to test instruments used on satellites and spacecraft, and to provide information about the Sun, stars, galaxies, and Earth's atmosphere and radiation. Sounding rockets fly in parabolic trajectories, re-entering the Earth's atmosphere downrange from the launch site. During this relatively short flight, scientific data is gathered and transmitted to a receiving station on the ground for analysis by researchers. The scientific requirements vary for each launch and cover a wide range of purposes. For example, satellite calibration, solar measurements, and student experiments are a few of the many purposes sounding rockets are used for. For this illustration, there are 6 phases from the launch to the recovery. Phase 1 is the launch. Phase 2 involves despin and payload separation. Despin is where a weight and cable system known as a yo-yo is deployed to despin the payloads. Phase 3 is boom or door deployment for science gathering. Phase 4 is at apogee, the highest point of flight. In Phase 5, the doors are closed or the boom is retracted or ejected. And then in Phase 6, the payload comes back to Earth and the payload and data are recovered. Oftentimes, the payload is reconditioned and reused.
What you're seeing is the view from the all-sky camera that is mounted in the roof of the Science Operations Center where we're currently located. As you can see right now, there's no aurora activity overhead. There's a few stars visible, but not much else. So we do have a pre-recorded video showing some aurora footage that was shot within the last year, and we'll go ahead and show that now.
Oh my. Oh my. This is incredible. This is just incredible.
Associate. Science. Yeah, could we get an update, please? Yeah, it just started brightening up behind the trees there. You can see it Venatize. It's still pretty far to the north, so we've needed to pull south. But it's still there. It's waving at us. We're watching it. How's that for a science report? It's better than your weather report.
That wouldn't take much doing, I don't think. Thank you.
Oh my. Oh my. This is incredible. This is just incredible.
And thanks to Neil Brown for providing that video footage of the northern lights. We were just talking as that video was playing about how the aurora appears to the naked eye versus how it appears on camera.
Yes, well, the sensitivity of a camera these days is much broader across the full range of the visible spectrum. The eye doesn't see nearly so sensitively in the red as it does in the green, for example. And then its sensitivity falls off as it goes further into the blue and violet. So we don't see such bright colors when we're looking at the aurora with the naked eye as the camera sees. That's one thing. The other thing is that those pictures of Neil Brown's that we were looking at, that movie, showed quite a lot of varied colors there. And those, we know why those colors are there. The green that we see is actually atomic oxygen, which is in the upper atmosphere. We don't get atomic oxygen here on the surface of the planet because it doesn't remain atomic. It recombines to molecular at this altitude. But up at the altitude where the aurora is occurring, which is some 60 to 100 miles, there the density is so low that collisions between atomic oxygen atoms are rare. So they actually have time to emit before they recombine. So that's for the green. We also saw in his pictures some violet, and that is that's nitrogen emission, and in fact it is nitrogen ions. So those nitrogen ions have been created by the incoming electrons, and they've ionized the nitrogen, so it sits there, and it will then recover from an upper state to a lower state by emitting that purple color. The nitrogen will also resonate with sunlight, and so sometimes you see a more continuous emission, and it's brighter because the sun is just keeping it going.
Okay.
Now, I didn't see in those pictures any red. Normally there is red in the aurora, but maybe this particular time it wasn't very bright. We have red emission that comes from atomic oxygen, and we also have some red emission that will sometimes be seen on the lower borders of arcs, which it comes from nitrogen, neutral nitrogen. So we know something about the altitudes that these things happen. Usually the bottom of an auroral arc is somewhere between 55 and 65 miles, depending on how energetic the particles are. And the top of an arc that you can see, well, again, depending on how sensitive the camera, but probably over 150, maybe 200 miles in some cases. So these are very extensive emissions, and they are in the form of a curtain. So people see this in the sky and sometimes don't realize that this is not a horizontal emission region. What they're seeing is a combination of curtains which are existing in the sky. Sometimes you just see one curtain, and sometimes you see several. And those curtains are very interesting if you ever are able to look at them from right underneath. You see a lot of structure. I tell people that what you need to think about is lying under the curtains at your window and looking up at the structure of a wavy curtain. And that's exactly a good analogy to what you're seeing when we're watching the aurora. Although, of course, there's a lot more detail in that structure than there is in a regular curtain. So the way in which these arcs are created is that there is incoming electrons and protons from the sun, and they travel in what's called the solar wind. And when the solar wind reaches the Earth, some of that, and usually no more than 5%, gets through the Earth's barrier, which is called the magnetopause, and it goes into the magnetic environment of the Earth, and it will eventually come down to form these curtain shapes. You'll see I say something like, well, eventually. It sounds like I don't know how. That's true. We really don't know exactly how these curtains are formed, although it's possible to do some simulation of it with a computer. In fact, we have a person working at the Geophysical Institute who does simulate auroral arcs, But I have to say that even though he does, this is not going to simulate exactly the arc that we see when we look up in the sky. So there's still quite a lot to be understood in how these particles are organized to come down in the curtain type structure that we see. But the particles come from the sun, and they are accelerated in the region of the Earth to be higher energy than they were when they arrived from the sun. Most of them are that create an aurora are going to be well, we use the energy unit kilovolts, and so they are between, let's say, 1 and 50 kilovolts. The more energetic ones come down lower, and the less energetic ones stop higher, and so you get this this formation of a curtain structure. They won't all get down to the lower end.
So it seems like there's a lot to still to be discovered about the aurora, and of course that's what we're working on here at the range with these two rocket missions.
And it's true also that you cannot really investigate the microstructure of the aurora without sending a rocket up, because you've got to be in situ to be able to make these measurements. Auroral arc, actually, these curtains are only about 1 kilometer across. They're about 2,000 kilometers long, and now I'm using kilometers, but okay, let's try and do that in miles. They're about 3/4 of a mile across, and they're about 1,800 miles long, and in height they're probably about 100 miles in height. So they're very, very thin in one sense, remarkably thin shapes, and the process that makes them that thin is still somewhat of a mystery. Oh, look, it's actually looking a bit better.
Okay.
See, this is
We're going to switch over to a view from the all-sky camera that is located in Venati, the area where Dr. Lynch is wanting to launch her rocket. And
so that's good. We're wondering, do you have an update? It's 11 o'clock. Maybe you, I don't know how many times you can call your meteorologist, but I just wondered if you had any update. Over.
I will call him.
Okay, thank you.
Okay. So what we're seeing now is the all-sky view from Venati. In this type of picture, you've got the horizon around the edge. So what you're seeing are trees which are in the vicinity of the camera around the edge. And in the middle of this picture, it's like you're looking straight up. And so what we're seeing actually are actually three systems of arcs. There's one that's running right across the middle and one running on the southern side and one on the northern side. And these are looking a little more hopeful than what we saw a while ago, that may actually want to launch into this. So I'd say that I'm not the PI of course, but I'd say that the situation that the PI is looking for is getting closer here.
And we just heard them also ask for an update from meteorology about the weather conditions, so they're probably trying to determine whether or not it's likely the sky will be clear long enough to
be able
launch
to
the rocket.
Launch the rocket, and they're not just going to get clouded over. Yeah.
So we'll go ahead and stay with this view for a little while. And we'll see if we get an update soon on the weather.
OC Science Report.
Go ahead.
So in general, we think we're more optimistic than we were an hour ago. The activity's starting to turn around and come back in the direction we like to see it. We've got some flows and we've got pieces of arc. We would like to see some more current, but it's looking promising, so we're hanging in there. Venati is still clear. Our beacon sites are clear, so we're watching.
Copy that. Thank you.
Radar 10 and balloon inflation. This is wind waiting on 3.
Balloon.
Radar.
Roger. We'd like to have another chaff, please.
Copy. Stand by. We'll call when ready.
Standing by.
Balloon is standing by.
Balloon inflation. This is radar on channel 3.
Go ahead, radar.
Can we have the flare swapped out for a 20-minute flare?
Affirmative.
Do you need much time for that?
Negative. I'm all set.
We'll pick it up on the next even. I have you 5-eye open sight. 1 minute on balloon. Do you want the light off? Thirty seconds on balloon. Open sight, I'm slaving to you. Twenty seconds on balloon. Ten seconds on balloon. 5, 4, 3, 2, 1. Release. Release balloon. Radar tracking. You're good to come in, open sight.
OC science report.
Stand by. She's getting the weather right now.
I don't really want to hear about the weather.
Go ahead.
Well, we're all standing here watching this. It's looking very promising, and we're waiting for our magnetometers to go boom so that we know that it has a little oomph to it. What we're seeing right now came up fairly quickly and could equally quickly go away. And so if we see the current signatures show up, then we'll probably drop the count. The flows are still good. The activity looks pretty. But without any current signature, it's hard to trust it. So that's where we're sitting. I think we have almost the whole science team in this one room. So we are all watching it. OC, let's bring it down to 3 and hold it there.
Radar, wind waiting.
Radar.
You can drop track.
Thank you.
Thank you.
Roadblocks 1 and 2, you can go on out. I'd like station checks on channel 2, please. PLC?
Go.
TM?
Go.
ACS?
Go.
RCV?
Go.
RDT?
Go.
Radar?
Go.
Surveillances, go. LO?
Go.
Cornell?
Go.
Dartmouth,
Go.
Pfizer,
Go.
Science,
Go.
MM,
Go.
CM,
Go.
RSO,
Go.
and the ranges go. Check 99.
Check 86.
TM, check 87.
Blockhouse, this is roadblock 1, radio check.
Copy 1.
Blockhouse, this is roadblock.
Copy 2.
1 is waiting at the front gate.
3, 2, 1, mark. We're at 10 minutes and counting for Lynch on pad 1.
Check 101.
Roadblock 2 is at front gate.
Check 102.
Check 103. Check 104.
Nine minutes.
1. 2.
20-footer has good. VTAR is looking good over here.
Roger. 8-meter has good VTARs. Roger.
Check item 94, 98, 99, 100.
Check 105.
Roadblock 1 is in position. Roadblock 3 in position.
Check 106.
Eight minutes.
1. 2.
Check 107. Check 108.
Check 109.
Seven minutes.
1.
Check 110.
2.
Check 111.
Roadblock 2 is in position.
Roger 2, thank you.
Check 112.
Five minutes.
1.
Four minutes.
1. 2.
Science wants to hold at 3, please.
Copy, hold at 3.
Check 115.
Check 116.
Check 117.
Check 118. Pad 1 launcher set. 81.1 elevation. 9.2 azimuth.
Check step 119.
Check 113. We are currently at 3 minutes and holding for Lynch on pad 1.
1. 2. 3 copies.
OC Science report.
Go ahead.
So this one may have fizzled, but we're going to sit here for a little bit. It didn't have a lot of current behind it, and so it just sort of was a flash in the pan. That said, it's all sort of poised, and so are we. So we'll hang tight here for a little bit and see if it comes back to us. You can see the arcs over Venati, but they're much less brighter than they were a few minutes ago. And if you're looking at the magnetometers, you see they had a brief excursion, but they've all come. They're starting to converge again. So we're going to look to the east of Venati and see if we see something coming at us from the east. Okay, so we'll sit tight for a bit.
Roadblocks 1 and 2, our latest science update. We are holding at 3. She said that this particular round may have fizzled, but we're going to sit and watch it for a little while.
1 copies.
Copy 2. Be advised, I do have somebody here. They're willing to wait a little while, but I told them I'd check back in a little bit.
Copy that.
3 copies.
Roadblock 2, Blockhouse.
Go ahead.
Go ahead and tell your traffic to go through.
Copy that.
Remind them not to stop, because if they stop, they were not going to be able to see a launch, because we won't be launching if they stop. And let me know when they leave your roadblock.
Roger that. I'm moving out of the way right now. They're gonna get moving.
Thanks. Roadblock 1, we'll let you know when they go past the front gate.
Roger that.
It's a little VW. They're on their way.
Thank you.
ACS, this is LO.
Go ahead, hello.
Am I free to move?
Yes, sir.
Okay.
Hello, ACS.
Go ahead.
Can you please call the new launcher settings?
Elevation 81.0, azimuth 9.6.
Thank you.
RSO confirms.
Roadblock 1, we see the headlights from the vehicle.
Roger that.
And they're just passing the gate.
Blockhouse to roadblock 1, traffic is clear.
Copy that, thank you. Science, SOCN 2.
Science.
The traffic is cleared.
Thank you.
ACS, LO.
Go ahead, LO.
Have new launcher settings.
Please go ahead.
New launcher settings, 81.1 elevation, 9.8 as.
RSO confirms.
ACS copies.
OC, we're going to recycle and hope that this one pulls itself together again in the next hour. Thank you.
Copy that. Thank you. We have recycled the clock to T-minus 10 minutes and holding for Lynch on pad 1.
TM, this PLC. It's TM. Ready to power down. Copy that, Brady. Just burn down all systems on the main and stuff.
Back.
Copy.
2 copies.
3, you can stay there.
TM, this PLC. It's TM. All systems are down with the exception of the buses and transmitters. Copy that.
ACS is off.
PLC, this TM. Go ahead. Go ahead and bring down the sub-bus and sub-transmitter, please. Copy. Okay, we have LOS on sub. PLC, this TM. Go ahead. Go ahead and bring down the main bus and transmitter, please. We have LOS in the main. Copy. All systems are off.
One is in the gate.
Copy 1.
Two is in the gate.
Copy 2.
Okay, people, once more round. OC, let's drop the count and hold at 3.
Copy that. I'd like station checks on channel 2, please. Roadblocks 1, 2, and 3, please go on back out. PLC.
Go.
TM.
Go.
ACS.
Go.
RCV.
Go.
RDT.
Go.
Radar.
Go.
Surveillance. Is go. LO.
Go.
Cornell.
Go.
Dartmouth.
Go.
Pfizer.
Go.
Science.
Go.
MM.
Go.
CM.
Go.
RSO.
Go.
The ranges go. Roadblocks 1 and 2, please check in.
1 is heading out.
Roadblock 2, please respond. Three, 2, 1, mark. We're at 10 minutes and counting for Lynch on pad 1.
Check
101. Waiting at the front gate.
2's en route.
Roger 2.
24 good VTORs.
Roger. 8 need to go VTORs. Roger. Check 103.
Check 104.
Nine minutes.
1.
Check 102.
Check 105.
Two is through the gate.
Roger 2.
Check 106.
I was fucking with the radio, slowing down instead of going 75. Oh, yeah. You know what I mean? I'm like...
Roadblock 2, watch your
Check
language.
107. Check 108.
Yeah, fuck you would have brother with fucking... Yeah, dude, that's why I'm like, fuck it.
Check 109.
Seven minutes.
Check 110.
Check 111.
Eight needed DREs in.
Check 9-4. Check 9-8. 6 minutes.
Check 112.
Five minutes. Four minutes. Check 113.
So science is going to hold at 3. So hold at 3.
Copy. Hold at 3.
Check 115.
Check 116.
Check 117.
Check 118. Fab 1 launcher, 81.3L, 8.1 azimuth.
Check 119.
We are currently holding at 3 minutes for Lynch on pad 1.
Science report.
Go ahead.
So it's like the little aurora that was trying to be an aurora. It's trying to break up, and it keeps having these little partial breakups. And we may have jumped the gun a little, but for the moment, I think we should just sit here. So
Copy that. Thank you.
ACS is LO.
Go ahead, LO.
I have new launcher settings, elevation 81.0, azimuth 9.0.
Copy that. Thank you.
RSO confirms.
Science report?
Go ahead.
So we're still watching it, but these little flash in the pan ones go by pretty quick, and our Veneti link croaked for 2 minutes in the middle of it. So we can sit here for a little bit. We think we probably missed it, but we're going to watch it for a little bit.
Copy that. Thank you. Roadblocks 1 and 2 and 3. We had a quick brightening of the aurora and it sort of died off again. So they want to sit and watch this for a while and see if it redevelops.
1 copies.
Copy 2.
3 copies.
Science update?
Go ahead.
So we're not sure whether it actually completely broke up, so it might still have something to give us. So we'll sit here unless there's reason not to. So if TM and OC can tell me if there's any reason I can't just sit here for a bit.
TM's showing all green board. Temperatures look good, so TM's good for a little while longer.
OC is fine sitting here, as is CM.
Thank you.
Science SOCN2. Could we get another update, please?
Yeah, we were just wondering how long we've been sitting here. We think it's been half an hour.
23 minutes and 29 seconds.
Not that you're counting. TM, how are we doing?
TM showing green board on external. Transmitter 2 for the sub is starting to heat up a little bit, but we're still below 110 degrees Fahrenheit, so we still look good.
We have nobody at the roadblocks. They're just kind of in the dark out there, so I need to tell them something.
So we're getting a repeating cycle of activity that comes and goes and never quite gets us what we want. And every time it does it, it's a little bit more so. So what we're arguing about right now is whether we should sit at 3 or whether we should recycle to 10 and wait for it to come around again. So give us a minute to ponder here.
Copy that. Thanks. Roadblocks 1, 2, and 3, they are still watching this arc, and they are trying to decide whether to sit at 3 for a while longer or recycle at 10 and see if it moves back where they want it.
1 copies.
2 copies.
3 copies.
So it's forming up again, but it's pretty far north, so we think that should it do its thing again, it'll give us a little warning as it moves south. So we'd like to recycle to 10, and I'll talk to Rob, and we'll decide about whether we want to try and take advantage of the clear skies against the cost of tomorrow. So for now, I'd like to recycle to 10. Yes? Yes, everybody's nodding. Yes. So please recycle.
Copy that, and I will see if I can get a weather report while we're back at 10.
TM, this is PLC.
It's TM.
Ready to power now.
We have recycled the clock to T-minus 10 minutes and holding for Lynch on pad 1.
Roger that, PLC. Bring down all systems on main and sub except for bus and transmitters, please.
Copy.
3 copies. 2.
Roadblocks, come on back.
Copy 1.
TM, this is PLC.
It's TM.
All systems are off with the exception of the buses and transmitters.
Copy that. PLC is TM.
Go ahead.
Let's go ahead and bring down the main and bus. Sorry, main and sub, bus, and transmitters, please.
Copy.
LLS on the sub. And LLS on the main.
Copy. All systems are off.
ACS is off.
Don Hampton, please call 2106. Don Hampton, 2106, please.
1 is in the gate.
Copy 1.
Two's back through the gate. Copy.
Copy 2.
OC Science.
Go ahead.
So we're going to buy another hour at the cost of tomorrow, so we're not done yet. And we're thinking we may be going around again here. Give us a minute.
Copy that.
CM, this is PI Pat 34.
Go ahead.
Yeah, just confirming what we've discussed on the phone. The Pfaff rockets have scrubbed for the evening, and my understanding is you're going to announce a report time tomorrow of 4 p.m., but I'll let you say it, and I guess we're also waiting on the snow forecast. Over.
Roger that. I was just getting the forecast now from Kathy, and she's going to go ahead and give everybody the update. But for everybody's benefit on the net right now, we are going to extend 1 hour tonight. As of right now, we're going to extend 1 more hour because we do have clear sights. We have something up there, and if it develops, we want to be able to take advantage of that. It does look favorable for tomorrow to work. I'm going to tell you that now based on what the forecaster said. Kathy's probably got a better synopsis of what that is, so we do need to figure what we want to do with our hours as well.
So I only got a partial weather forecast because when I got a call from Science, I thought we were picking it back up again, so I hung up on them. But evidently there is going to be a big system moving in that's going to pretty much blanket the interior by midweek, at midweek, probably Wednesday. There will be some snow showers around prior to that. But the earlier forecast that we had for the wide swath of pretty solid clouds coming in, that was going to cover from the west almost to the Canadian border and then from a little south of Fairbanks all the way up north. It's a pretty weak upper low. It's moving very slowly. They said it's deteriorating as it moves, so we may very well see conditions tomorrow like we see tonight, depending on how big the holes are and where they are at the time we need them. She said Thursday, when this big system comes through, is probably going to be the worst day of the bunch at this point, and that's pretty much where I hung up on her because I thought we were going to pick up the count again. But tomorrow has improved significantly from the earlier forecast.
Thank you.
And for the Pfaff team, report time will be 4 o'clock tomorrow.
PI, this is CM, Christina.
Yeah?
If we let the Pfaff team leave, is that okay now, or do you want me to get them if they come down the hill to stop here at the blockhouse in case you pick it up?
I think we're on a sort of 10-minute cadence here, so it'd probably be good if they were to check with you.
Roger that. If any of the Pfaff team wants to leave, I mean, Ted's the one that's got to tell you that, not me, but if you are going to leave, I want you to stop by the blockhouse before you go out that gate in case we need to keep you here. And then we'll get everybody to leave at once.
.301 TM, this is 301 PLC.
Yeah, and anybody that wants to leave, Ted, anybody wants to leave, don't dilly-dally, just go ahead and get out the gate.
301 PLC, TM.
Go ahead.
Yeah, you called?
No, he meant to call 306.
306.
Go ahead.
Am I clear to shut off heaters?
Yes.
Heaters off.
Copy that.
ACS, this is Hello.
Hello, go ahead.
New launcher settings, elevation 81.1, azimuth 10.0.
ACS copies that. Thank you.
RSO confirms.
OC Science.
Go ahead.
Okay, we're done for the night. Thank you, everybody, for bearing with us. We look forward to a better, well, I mean, it was pretty good stuff tonight. It just didn't do its thing. And we're looking forward to better weather for Dr. Pfaff tomorrow night. Thank you.
Copy that. Thank you. RF avoidance is now in effect on all pads. No switching on any pads. Radar, did you copy?
Radar copy.
Thanks. Attention all personnel, we have scrubbed for the evening. Station time tomorrow will be 4 p.m.